Good morning, everybody. Joining you in just a minute. Making sure all of my stuff is working. Got my little Wacom tablet. Got my cup of coffee. Got a new desk mat on my desk here at home. I was looking at pictures of desks on Reddit, and everyone has these nice leather mats. So I've got this thing. It's not leather. It's plastic leather. Plastic that looks like leather. I'm not sure whether it's definitely more vegan but less sustainable, I suppose. But I wonder if it actually makes the sound better, because it feels like it's kind of deadened my acoustic environment down here. Down here in the COMP2300 studios. Now, get myself back to the very first page. I've got a few people watching on YouTube. Thank you for joining me here this morning. I'm going to start my recording. I'm going to say, good morning, COMP2300/6300. Great to join you here on this slightly colder than last week Canberra morning, Thursday. I don't even know what the date is. Thursday, 17th of March, 2022. How time flies, hey? We've got another good lecture here for you today. Another exciting and interesting adventure into control structures and how they might be used on your microbit. Before I do that, I'm just going to check on the team to see that people are available. I think they're hanging out with me. Where's my team? Team. That's the wrong team. Oops. That's team. Lecture is on. Come join in. So today, I suppose we had this whirlwind tour through control structures earlier in the week on Monday, and that was a lecture that I know many people missed, because it wasn't a Monday lecture, it was on Tuesday because Monday was a public holiday. It's recorded, ready for you to watch on YouTube or Echo 360, so very happy to have you watch that. I'm sure that many people have done so already, because it's really critical knowledge. It's absolutely core, not a lecture which we can just skip. What we have today is kind of the slightly slower sibling that's going to just pack in the information and make sure that everything is squared away. We're going to do a really cool worked example related to string processing in assembly, which is something which is extremely satisfying when you see it working. You really feel like you know what the computer is doing when we do this. I will just mention before we start, as always, please, if you haven't done so recently, look at the assessment page. It is now week 4. Assessments are becoming real parts of life in this course. They were always real before, but they were in the future. Now they're in the present. You've already had an assessment, which was the lab, Pack 1. You've got a quiz on this week. I know that there are many people trying the quiz. Last time I looked, there were 500 attempts on the quiz, which is great. We have only 400 people in the class. So there's many people doing it many times, which is wonderful. The assignment pre-submission is due next week in your lab. Oh, excuse me. A COMP2300 sneeze. If only we could sneeze in assembly. I was too slow on the mic mute button. I need a little sneezing button over here, like the podcasters have. It's as if I was in a lecture theatre, I could blame it on chalk dust, but I can't. I can only blame it on just sneezing, being sneezy. Okay, so let's get to the lecture. Make sure you look at the assessment page. Do it now if you haven't done it already. Control flow. I'm just going to breeze us through the... Someone said they did about 10 attempts for the quiz. Thank you. Great. Great. You did 10 attempts at the quiz. That would have made it a really valuable learning experience for you to go through, see which answers you're getting right, which answers you're getting wrong, and really have gotten a lot out of it. So I'm really pleased that someone's told me that they've done 10 attempts at the quiz. It may seem like that's crazy, but that is what I hope you do. I hope you use it in whatever way makes sense for you. If someone goes through the quiz and gets full marks first time, well, great, I didn't have to teach them anything. They just knew magically. But for those students who are not getting full marks each time, I'm giving you this quiz as a chance to really look at those topics in detail that you feel like you're a bit weaker on. Okay, control flow. We talked about three things, well, two things, conditionals and loops on Tuesday. Conditionals is the if then else construction. And loops are very similar. They use a conditional to decide whether to run a block of code, and then they go back to the top. So you're iterating on a conditional, basically, in a loop. We talked about what we could call the best if-else pattern. The best if-else pattern in assembly. I mean, you can do whatever you want in assembly, but this one is it's a really good way, a really good thing to remember as a basic way to do this if you don't know what you're doing. The first thing you do is you run some test that sends flags. If the test passes, then you'll want to do a conditional branch to a then label. And remember that once we've run the then label, our program will just keep running straight on into the rest of the program. We don't have to do anything else. If the test fails, we drop down into the else label. We don't actually need the label there. And then we do some stuff. Then at the end of the else label, we have to do another branch. If we don't, we'll start running the code under then. And that will take us to run the rest of the program. So it's really important to remember this way of doing things. You must guard against your code jumping down into the wrong block. Then we talked about loops, and there were two kinds of loops which were really important that we talked about. The first was a while loop. Here's an example of a while loop. We have a loop body, and we have a testing area at the top. So we do a test, we set some flags, do a conditional branch into the while loop if it's true, and if it's not true, we go to the end of the program or the rest of the program. And we did talk about how there would be a way of just using one branch there, which would be that you invert the conditional check. So you're checking on the else case. That's escape the loop. Then the last thing we looked at was this for loop concept. For loops are similar to a while loop, but they have a built-in facility for having some counting number or an index to count your iterations. So if you want to loop 100 times, it's often a for loop that you'll choose because it will give you this little way of constructing 1 to 100 or setting up a variable, setting up a test condition and setting up a update command. So we ran for loops in assembly as well, where we set up an index register. Then we basically run the same code as the while loop, except that at the end, just before we go back to the top of the loop, we update the index register. So we do something like add R0, 1. So that that's not an I, it's a 1. So we're incrementing our index register. And then we did a little worked example, odd sum. This is in the slides now. It wasn't in the slides before, but I took the code I wrote in the lecture and wrote it in the slides and added some comments. So you can use this code to check your understanding of how to write a for loop in assembly. And I will say this right now, every COMP2300 exam and mid-semester exam in the past 5 years has had a question about translating some code in Java or C that uses a while or a for loop into assembly programming. So you can be very sure that I will probably ask this on an exam again. And you can be very sure that I will not be giving full marks to things that aren't actually a while or a for loop. That's the biggest problem I see when I ask this question. Write me a for loop. If it's not quite a for loop, it's not clear that you have that understanding of how to turn that into assembly, then it's not full marks. Whoops. Okay, so now we get to go to the content for today. We're going to work towards another worked example in a minute. I'm just going to show the worked example now, or what we're doing, and you'll feel excited, and we'll get back to it in a minute once I've just done a few extra slides. Probably this example should be a bit further in the lecture, but it's here now. So the demo we're going to do is looping through an array of characters. So in your microbit, when you store a string, that is what you would write in Java as like, this is a string. These get encoded in memory as individual letters. Space is space a space string, etc. So we're going to load these characters from memory one by one in a loop, turn them into a capital letter, so that T needs to get turned into a capital T, that turns into a capital H, capital I, and then store it back in memory. So we can take a string stored in memory, make it capital so it's shouting the same thing, and store it back in memory. This will require a loop. It will require a bunch of conditionals to do some checks about these characters, and it will require memory operations as well to load and store in memory. So we'll just go do a few more slides which kind of revise a few of these memory operations and concepts that we've been talking about, and then come back to this demo in a minute. So, oh yeah, we'll talk about this IT block thing in a minute as well, maybe after the demo. So recall memory. We've got this big memory map where we store memory in different locations, and I think you'll recall from last week when we talked about memory that the RAM that we use starts at this address, 0x20000000. It's sort of dropped off the bottom of this image there. Sorry about that image. So when we want to load something from RAM and store it back, we can just use those raw memory addresses. But you also remember that we started to use this .data directive, and you've been doing this in your labs, the .data directive, to store data in that RAM in different places. And what we now know from our talk about labels is that you can store the memory address, use a label to get the memory address of something in your code. So if you have a .data section and you've put a word of data in memory, then you can use this label to get the address of that data in memory. So in this case, because it's the start of the .data section, that address is going to be 0x20000000. But you could have all kinds of stuff down there, and we might not be able to read the address so easily. So it's useful to be using labels a lot to access things from memory. That's how we find things in memory that we've put there as a constant. Now, talking about these value directives, you've used these already, you've seen them in your labs. I just want to put them out here just for clarity about what they are. These are the ones which we talk about in COMP2300. I think there are probably some more, but we use these ones all the time. So these, this directive tells your assembler not to actually assemble something. So if you are giving your assembler an instruction like add R0, ... it's going to turn that into, your machine code, some ones and zeros. These directives say, don't do that. Take this number I've given you and just plonk that straight into memory, save it there, and I might need it later. So this putting of things straight into memory is a theme for the next few slides. We can put a byte straight into memory. How big's a byte? It's going to be something like this, 2 hexadecimal digits. 0x12, 0xAB, that's a byte. We can put an H word into memory, that's 2 bytes, 0x1234. We can put a whole word into memory, 4 bytes, 0x11223344. We can put, and this is more where we start to do some fun stuff, we can put letters in memory encoded using the ASCII system, which turns them into bytes. So we can say .ASCII, here's some text, and it will turn those into numbers and put them in memory. And we did that a little bit in our memory lab, I think, or our memory lecture last week. I think I did these examples of putting some long sentences in memory, and then when I ran my program I could see that each letter had been encoded as a different ASCII, a different byte. If we want to know what these bytes are, I'm giving the game away here because I've got my example in front of me. We can see the table for the ASCII character set here. So there's lots of stuff here which is not very useful. The ASCII character set is designed at a time when computers as we know them didn't exist. There would be mainframe computers, there would be terminals that could access those computers, and most of these terminals did not have a screen, they had a kind of typewriter. So you would type some stuff and press enter, and what you typed on the typewriter would go into the computer. So a lot of the ASCII format encodings are dedicated to special commands that are useful if you're trying to remote control a typewriter. Start of text, end of transmission, start of text, start of heading, null character, inquiry, acknowledge, the bell, ding, carriage return, form feed, vertical tab, new line, horizontal tab, backspace, bell, shift in, shift out. All of these things are like very much to do with typewriters, which is weird that we think of computers as having anything to do with typewriters, but they very much did for quite a long time in the history of computers in the 20th century. Now we get to the characters which are really useful over here, starting at hex 40 or decimal 64, or 65 we get capital A, that's a good character. 66 is capital B, 67 is capital C. Then down here we've got a bit more punctuation, and then the lowercase characters, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, all of your friends. Do we have any characters from non-English languages in here? No. Why is that? Because colonialism, I'm sure. It was just an American-focused, North American-focused, English language-focused standard for storing data. This has the advantage here of being able to store all of the store all of the English letters and these characters related to typewriters in 1 byte, which is a fairly compact way of storing things. If we have to store a lot more characters, we have to use more memory for each one. So it's still in use today because of this convenience of just being able to fit all the letters into 1 byte. So that's ASCII. Someone's asked a question. I'm going to go to my team. And someone is saying, use AskIs to do something. Yep, so AskIs is going to do exactly the same thing. Insert an ASCII encoded sequence of bytes followed by a 0. Now, it might seem weird. Why would you do that? Well, as it turns out, there's no, in ASCII, 0 doesn't mean anything. Well, it means the 0 null character. So it's not used for anything. So it means we can use it to say, this is the end of my string. And in fact, it's so common to do this that we have the assembly directive AskIs to let us do it. If you make a string in Java or C, it is in fact a 0 terminated string, a null terminated string. Actually, I'm not sure about Java. I presume it's the case. But definitely in C, if you make a string, that is a 0 terminated string. It is just using AskIs or something like that to make that string exactly as a sequence of bytes in memory followed by a 0. We'll investigate this in a minute when we do the example, but I just want to let those ideas simmer in your head. It's great that someone jumped ahead and suggested that we would be able to use this 0 to know when our string has ended. Exactly right. Someone else has said, is each ASCII character a byte in memory? It is. So each ASCII character is stored in 1 byte, which is a very convenient way to do things because our memory is byte addressable. We can look at 1 byte at a time. Okay, a few tricks about these directives. You can use them to insert multiple values, one after the other. If you just say .byte, you can just put in a list of bytes, 4 bytes total. You can use them to insert some half words after the other and some words after the other. And of course, you can also just use the ASCII directive to enter in multiple letters at a time. I think this is the last thing we really need. We've talked last week about load and store using a memory address in the brackets, but there's this version, the offset version of these instructions. So you can add a comma after your register which holds the memory address. R0 is the register where we're going to load something into. R1 is the memory address. We can say, instead of loading something at R0, at R1, we can say load it at R1 plus 4. So R1 is a memory address indicating 1 byte in memory, and 4 is going to be that moved along by 4 places, so the 4th byte after that. You can also do negative numbers, R1, comma, -4. Now, can you see how we might use this? If we had a list of something in memory, so our memory kind of looks like a sequence of little containers, and this one might contain the letter A, B, C, D, E, F, G, H. So this one, we could call that one, its memory address is going to be stored in R1. We can also write it as R1 plus 0. This one could be R1 plus 1, and that one's R1 plus 2. Oh, now this is useful. So now we could access any of these bytes, any of these letters, by doing a load R0, R1, and then some offset here. Suppose we put that in R2. Can you see where I'm going with this? So if we do a loop for something like that, for 0, R2 equals 0, R2 less than 10. I don't know, I'm just saying perhaps there are 10 characters to look at. R2++, liter R0, R1, R2. We could loop over the value of R2 and extract each letter from memory one at a time. How cool is that? Someone's asked, can you store multiple strings with one? Oh no, my head's in the way. I'll move over this way. I'm going to fall off the page, I think. Can I store multiple strings with an ASCII label? I think you can. I believe so. We can test that in a minute. There's the... I mean, I'm going to do this in code and on a microbit in a minute. You'll really get it when we do it that way. But yeah, so this offset is going to allow us to select a particular byte in memory to grab. And this is where the way that memory is laid out in this byte-wise fashion becomes really useful. Okay, I'm not going to do a talk right now. You're talking in the chat. If you've got an idea, just chuck it in the chat. Let's do it. Looping through the array. So, I don't need Docker. Just because I have Docker on my system doesn't mean that I want Docker extensions in VS Code. Or do I? Is it possible to offset by a number of bits? No, it's not. Memory is at minimum byte addressable. It's not bit addressable. Oh, excuse me for a sec. Yeah, so memory is byte addressable memory. You can't select one particular bit out of memory. We can only select a byte. I'm going to delete all of this and start from scratch. So, let's make a slightly smaller string. I'm just going to compile my program just to show you what the memory looks like with this string there. Actually, I wanted an ASCIIs. Ah, no. ASCIIs. There we go, ASCIIs. Okay, so our program's running. This program doesn't do anything. Ooh. It's got no instructions. I should put a NOP in there, otherwise this is getting confused, I think. But nope, no, a NOP. And we'll view memory. OX2000. So it wants 64 bytes. So here is my memory view. And helpfully, the memory view shows you the ASCII decoding of your memory. It's very frequent, very common that a memory viewer will let you do this because often you have little bits of ASCII text in your memory that is just helps you see where things are, even though most of your data doesn't have an ASCII encoding. So there's the letter H, capital H, E, R, E, apostrophe S, 20 is space. We'll go back to our ASCII list and just verify that. Oh, it's 20, not, it's hex 20. There it is, space. Sorry, these are hex numbers, not decimal numbers. There you go. So our incredibly long sentence has been encoded into bytes in memory. So far, so good. So now I need to get into this memory. So let's just start hacking. First thing I'm going to do is liter in the address of my string. using the lit pseudo instruction. We'll talk about that again in a minute, but we've covered it already. This is a good way of getting a label, the address of a label, into a register. So R0 is the base address. I won't use R0 for it, I might use something higher. How about R4? And letter R5 is going to be my offset address. Okay, now just for kicks, let's load in one of my letters. Whoops, what's going on with my error 1? What did I do wrong? So it's going to be something, isn't it? What have I done wrong here? Maybe it's too early in the morning to be doing complicated examples. I don't think it can be. We'll get just out this string in a minute. Someone's going to tell me on... Oh, I've done it wrong. Should ASCIIs be indentized? No, we don't need to indent ASCIIs. That worked already. Oh yeah, move R50. Sorry, this. I should look at line 7. Stop, look, and listen, Charles. You should be telling me. Look at my errors. Look at what line it says there's an error. Line 7. What's wrong with line 7? It should be a MOV. Of course. Silly me. Okay, we'll get this show on the road in a second. I don't want Cortex peripherals, I want Cortex registers, and I want to see what gets loaded into R0. Well, there's a thing. So I loaded something into R0, but rather than getting one single byte, I've got a whole word. I've got capital H, E, R, or something, E-R-E-R. Doesn't seem right. Capital H, oh, it's a little Indian. There's my capital H, there's my E, R, E. So that's could be fine, but I don't really need to load all of that information. So in fact, what I'm going to use is the load byte version of letter. You can just use letter to load in 16 bits, 2 bytes, or just 1 byte. So I'm going to change it to letter B and test out. I just want that H, not anything else. Get my string, that's my label address is the typical 2 followed by 7 zeros. R5 is 0, and load in, and I've got just my H there. OX48 is the encoding for H. Now I'm just going to move along one single letter and get the lowercase e. The H is already uppercase, isn't it? So we'll get an lowercase e. Here's a lowercase e, OX65. Let's have a look at the ASCII table. I know people are in the chat getting excited about how this is going to work, because this is the first real program we've written, I would say. Like, it actually, you have to think about what we're doing here to get this to work. So I'll draw your attention to the fact that all of the uppercase letters are all offset from the lowercase letters. So we can change a lowercase letter into an uppercase letter by changing the number of its representation. So if we had 97, that's a lowercase a, and decimal 65 is an uppercase A, 97 minus 65 is 32. So if we can take out 32 from our lowercase letters, subtract 32 from them, they'll turn into uppercase letters. Let's just look at E, OX65 or 101 in decimal. 101 minus 32 is 69 in decimal, and there we have uppercase E. And it works for all of them because they're all the same offset apart. Now, someone in the chat, I'm going to ask you a question and you're going to answer it. Someone come up with a clever way of subtracting 32 from a register. Think of all your cleverest ways. There's 1,000,001 ways to subtract 32 from a register. So I want to hear about it. In the chat, you can go and do that. I'm going to do the boring way, and if you come up with a cool one, I might use it in the example. So back to our Visual Studio Code. We've loaded in an E into R0. Now I can do sub R0, R0, 32. And I should have that a representation of an uppercase E in R0. And now I'm going to just do the opposite of my load. I'm going to store it back. Store the adjusted letter. So let's try my program. I'm going to want my memory view as well somewhere. View memory. Oh, invalid length. Come on. OX2, 1, 2, 3, 1, 2, 3, 4. Nope, not the right offset. I'm not having good luck with my keyboard this morning. Memory. OX, 1, 2, 3, 1, 2, 3, 4. There we go. So load my offset and my base address, load in my letter E, 65. It's that 65 we're talking about. And there it is as a lowercase e. I'm going to change it to a OX45. And then I'm going to store it back. Bam. And now I've got, if you look in the memory viewer, an uppercase E, HE. So if we can do it for one letter, we should be able to do it for all the letters. So now I'll make my loop. Someone suggested somehow make the fourth bit from the left 0 if it was 1. I'm going to say, what about the bit clear? The BIC operator. I'm still waiting for someone to tell me a clever way a different way of removing 32 from a number. Now I'm going to make my loop, and in fact it's going to be more like a while loop because I've got an offset here, and I'm going to loop. It's kind of a weird combination. My offset will sort of be like the index. I guess that makes it a for loop, but I'm not using that index directly to give me the stop condition. The stop condition is when the byte I've loaded is 0. So we're going to need to put in our check if R0 is 0 here. But let's start with our loop label. And just change that to 0. Okay, first we do our check. compare R0 with 0. And if they are the same, BQ, we jump to a label down here, which is going to be exit loop. So far so good. We've got our loop. We load in the letter, check if it's 0 or not. If it's 0, that means we're at the end of the string. We can exit the loop. If it's not 0, it means we need to deal with it. Change the letter. And then we do add R0, R0, 1, no, not R0, add R5. Increments the offset. And then go B, loop, back to the top of the loop. Okay. Let's see how this works. Everything should be fine, right? I can't imagine that there's any problem with the code that I've just written. Someone's saying in the chat that there's problems with my code. I'm not looking right now. I don't need to hear your negativity right now. My code is perfect. We'll find out what happens. Okay, we've got loading the first letter. We load in OX48, that's an H. Check if it's 0. The 0 flag is 0, so we're not looking at the same number. We're not going to follow that BEQ. Now I'm going to subtract 32 from that, 28, store it back. Keep going through my loop a few times. In fact, I'm going to put a breakpoint in here and just go to the breakpoints. All right, so how did we go? How did we go? I think we probably stopped in the right place, and some of our stuff has worked. The H has worked. The H didn't work, it turned into an open bracket. The E and the R and the E worked. Our spaces may be a problem, because our spaces have turned into a 0, not the OX20 we needed them to be. So spaces aren't the same as 0. Spaces aren't the same as null. Spaces are their own character. So we've removed 32 from the space, turned it into a null character. That's bad. So we're going to need some more stuff. We're going to need some more control flow in here to make sure we only change the letter if it's a letter that we care about. So what makes a letter that we care about here? We'll have a look at our encoding list. Letters we care about have an encoding greater than or equal to 97 and less than 122, less than or equal to 122. So I'm just going to type it in the chat so I remember. Need to choose letters greater than or equal to 97 and less than or equal to 122 in decimal. Okay, back to, so we can do some ifs. Stop my code. Let's do an if. We've got that R0, so we're going to compare R0 to 97 and whoop, what was our best way of doing it? We did the if first, then the else, and then the then. So this is the then, is the then is going to be the change letter, and the everything, the continue code, is the increment offset. So change letter is going to need to have its own label. That's the then. The else, we don't have one. So we could compare R0 with 97. I suppose we could go straight to what should I be doing? If it's less than 97, we should go straight to increment offset, and if it's more than 122, we should go straight to increment offset and skip change letter. That's probably the best way to do it. LT, B less than 97, means we go straight to increment offset. CMP R0, 122, B greater than, straight to increment offset. Okay, so we didn't need to have that change letter, that label there after all. So we're going to load up our letter. We're going to compare it to 97. If it's less than 97, we're going to skip the changing the letter bit. If it's more than 122, skip the changing the letter bit, go straight to the increment part. If it's in between those two numbers, which is the only option left, we subtract 32 and store it back. Let's try it. Into our loop, loading in 0x48. It's the big moment. Is it less than decimal 97? I should probably put that in as a hex so we can more easily see which ones these are. 97 is 61. And 122 is 0x. Just human me, 7a. Loaded in 0x48. That one's definitely less than 0x61. So it will be skipping our code for changing the letter, going straight to the increment offset. Good. Going back to the top, loading in 6.5, that's definitely more than 0x61. So we're not doing that, not doing that. We change the letter to 0x45, store it back, and we get a capital E. Now we are in business. We get our lowercase r, transform that, store it back. You can see the letters over in the top right changing as I go. Now we've got our 0x27, that's the apostrophe. Didn't do anything with that, that's good. Loading in the S, 0x73. That's definitely going to have to be changed. Yeah. Loading the space, 0x20. That one doesn't have to be changed, it's left there. Cool, I'm just going to press start, continue until I exit the loop. And see, we'll know it's worked if this exclamation mark at the end stays as an exclamation mark. I put a breakpoint in at the end of this loop, just so that we know we stop. Here's an incredibly long sentence with an exclamation mark. Folks, it looked like it worked. It looked like it worked. What about that different way of doing subtracting 32? We can use the sub instruction, but you can also use a logic instruction because 32 is a power of 2. You can just cancel out one of the bits in that. So I'm just going to imagine it could be bit clear, R0, R0, and I'm going to, you could also just use 32. I think that will have the same effect because the number 32 will just have exactly that one bit set. I think you can also do that, put in your shift. Will that work? I always forget how to do the shifts in assembly. No, not 32 bits. It's the fourth from the right. 1, 2, 3. Yeah. 4 places. 2, 4, 8, 16, 32. 5 places. So 16, 32, yeah. Whoops. Did the same thing? Yeah, so we got it right. So that's another way of subtracting 32. Another way. Cool. All right. Well, I feel like that was a decent task. Any feedback or thoughts about that task or questions? I'm going to give another few slides before we stop, but I've actually been looking forward to doing this because I think that this example starts to show how all of the parts work together in the microbit within assembly. You need to use these control structures, these conditional execution, conditional branching commands to do your if-then-elses. You're using loops for many things, but one of the main things you use loops for, the very main things, is to go through memory and do something over and over again. Because your microbit has this huge amount of memory. It seems small when we compare it to big computers, but our desktop computers now have just incredibly, unimaginably vast amounts of memory. But for the microbit, even then, it does seem huge. You can't just pick one byte at a time and do something. You have to set up a data structure and iterate through it to do things. And an array in assembly, an array is simply a sequence of memory stored variables or things that have a certain equal length. So this is an array of bytes. It was very easy to go through that because each one is a single address. You can have an array of words, an array of half words, an array of 64 or 128-bit numbers. It doesn't matter, but you have to make sure that your offset is much bigger in that case. And we do have a whole lecture on data structures later on. This is our just little taste of how you can store a data structure in your microbit. But what a useful data structure it is. A string is a really useful data structure. You can also think about this as an array of bytes, a zero-terminated array of bytes, and store some other data in it that's not meant to be a string. So this brings loops together, it brings control structures together, it brings memory together, it brings labels together. All of the concepts we've been doing, conditional execution, arithmetic operations, everything we've done over the last 4 weeks comes together in this example, which is why it's so useful and cool. This doesn't work. Someone's saying that something doesn't work. Do you mean the bit clear doesn't work if there's no 32 in that place? Like, it only works because the numbers you care about are in the right range. I suppose that's possible. It's a really good question because it's breaking my brain a little bit, trying to trying to express why that would be the case. Hmm. Very good question. So the question is, I'm going to have to take this one on notice. The question is, are there numbers bigger than 32 that you're going to then have trouble subtracting 32 from? So these numbers are in the right range, right, I suppose, where there's always that 32-bit set. So there's always something to subtract from there. So the BIC works in this case. It probably doesn't work in general for all numbers. If you just had the number 64, you can't subtract 32 from 64 by clearing bit 5. But you can with these particular numbers. So I think it's a trick with these particular numbers that is making it work. Yeah, so I guess this is this. I didn't get that. Oh, it's always Siri. This trick only good for ASCII text. That's what my disclaimer I'm going to put there. I think there's something about the way that ASCII is designed, such as this trick works. Like those letters have not been put just randomly in there. They've been put in particular ways so that there's an easy way to change between uppercase and lowercase. But I'm not an expert on ASCII history, so I'm not going to comment any more on that. It's a good question for Piazza, and then the tutors can tell me if I'm wrong. Yeah, but very good point. There's e.g. if you have 64, which is going to be 64, 32, 16, 8, 4, 2, 1. Clearing the 32-bit. 1, 2, 0, 1, 2, 3, 4, 5. Yeah, okay. Anyway, just having some fun with arithmetic and assembly instructions. It's good to ask these questions and figure out what will work and what won't. What are we left with? A few things. Something I want to talk about, IT blocks. I've got 15 minutes more to talk. I know some people are going to a lab, but I just want to do this one little bit. Have you ever noticed that there are these little condition bits on lots of instructions in the cheat sheet? Lots of instructions. So, for instance, all the arithmetic ones have, well, these possibilities of putting in a C. Well, maybe none of them are listed there, but on the PDF cheat sheets, they are. Where's the PDF one? I need to make this more sensible so they're all in the same place. The PDF cheat sheets, there we are. We've got this add C. We should be able to do add EQ. But if you try to put in add EQ, R1, R1, 1, it actually doesn't work. Your assembler says something wrong. It says error, thumb conditional instruction should be in an IT block. Add EQ, R1, R1, 1. Well, that is not very helpful. What's an IT block? Well, this is a little ARM processing trick. It's another one of these ARM ISA tricks for letting us do conditions on any instruction without having to make the machine instructions longer in memory. Remember, there's a lot of compromises in ARM ISA about having small instructions that are only 16 bits, mainly those 16-bit instructions. And trying to focus on that means that there's just not enough space in the machine encodings to have special features like conditional execution on any instruction, but that would be a useful feature. So it just doesn't fit into 16 bits to do that. But we have this concept called an IT block. So there's another instruction here, IT, which sets up a kind of mini if-then-else statement for you that can have up to 4 instructions. This is not going to be if-then-else with like really big blocks of code. It's literally if the then can be one instruction, the else can be one instruction, and then you can have a couple of other thens or elses. So you have to say what the condition is. In this case, we're going to use EQ, and then which instructions are going to be thens and elses. Here's an example. So we're going to compare R0 and 42. We're going to set up an if-then structure. So just one command, one instruction which will run if the condition, which is equality, is true. So then we're allowed to run add EQ R1 R1 1. I'll just show you how that works prove to you that it works. I'll just put it in at the top here. Okay. Compare R0. R0 is just some big number. Compare it with 42. They're not equal. The IT runs. And then the add EQ should be adding R1, adding 1 to R1 if it's true, and it just skips it, didn't run it. So that was what happened. But in fact, if I run again, and you can actually go into variables here, change R0 to be 42. I'm going to change R1 to be, I don't know, 0, just so we can test. Compare R0 with 42, do the IT EQ, and then add EQ R1 R1 1, and it actually did it. It added 1 to R1. Did you know that if you go into the variables area in VS Code, you can just change the variables, change your registers while your program is running, which is pretty cool. So there's a very simple version of this concept. You can do more complicated stuff. You can add up to 3 thens or elses after the IT. So here's an if then else. ITE EQ. If R0 is equal to 42, we add 1 to R1. If it's not equal to 42, we subtract 1 from R1. So this is a very compact way of just doing a little if then else with a number of just one instruction for each branch. And there's a link to the architecture reference manual or a Stack Overflow question for more info about how to do that. It's really useful. It's a little hack. How does it actually work? We could say it uses some bits in the IT instruction. I suppose I do this one. Add, no, not increment, ITE. When you run that, it puts some information in the program status register to store that little plan. So the if-then register gets a number that stores its configuration of then and else. I've forgotten quite how that works, but it uses about 3 bits or something, or 4 bits, just to say which things should be ifs, which instructions should be thens, which should be elses, or there's only one if, and what the condition is. So we'll have to look in the reference to get the full story, but it's a very useful technique. Okay, and the other slides I have here, what else have we got? Putting values in the instruction stream. You've already tried this out in Lab 2. Putting your words like dead beef right in the instruction stream. A good question would be, what does this program do? Which address does the PC register point to? So PC currently points to that branch instruction. PC plus 4 is probably going to point to directly to this word dead beef. Moving along 4 bytes. That align to make sure that the following label or directive is put into memory on a 2-byte offset. So this idea of storing data in your instruction set and loading it in with this kind of design, this sort of instruction pattern, load and offset from PC, is really, really useful. It's also really hard to do by yourself because it's very annoying to have to calculate offsets from the program counter manually and put it into the assembly code. So it's such a useful trick that you actually get a special syntax to do it. So this liter R2, comma, equals something is a pseudo instruction to help you load any arbitrary data into R2. And in many cases, the way that it does that is by leaving a constant in the instruction stream to be picked up by an offset from PC. So it's called a pseudo instruction. The reason it's called a pseudo instruction is that although it looks like a letter, and in some cases it does end up being a load register instruction, if you put a number here which doesn't need to be stored in the instruction stream, it will just use a MOV instead. So there's many ways that it can actually accomplish its goal of getting a number into a register on your behalf by whatever trick is necessary. So it's really, really useful. We can use disassembly just to find out how this works. This was one of the last little demos. Put that into the instruction stream here. Compile our code. And then what I will want to do is look at the disassembly of this function to see how it is actually used. Main. So there we go. It's put something into assembly, but it's put it as doing an offset from PC, but it's a long offset. So it's adding 44 in decimal, annoyingly, down here somewhere. I don't have a good calculator nearby which can turn decimal into hex. 44 in hex is 2C. So it should be 2C. Where's my dead beef? That's gone. Oh, I must have put it in the next instruction after that. So I'll have to use my memory viewer to find it. Oh, it's just stopped my program. View memory, OX200. And like, I don't know, 256 bytes. Where's my dead beef? That's going to be hard to find, isn't it? Yeah, anyway, it's put it, oh, there it is. Dead beef. So it was there all along. It was stored after the end of this main function. Dead beef has been stored to be used later by me. Okay, finish these slides off. Why dead beef? These are just like things that look cute, words that can be expressed with hex numerals. 8 bad food is another one, very popular. There's a whole list on Wikipedia if you're interested. Nothing particularly special. The last thing we're going to talk about is labels, another little point about labels. And you've seen me many times use this pattern for loading a label, the address of a label into memory. And this example shows an instruction loading its own address into R0, which is a bit meta, but there you go. And the question is, how does your microbit know which things are code and which things are data? So the microbit doesn't care about code and data. If you put H words into your function, you can do this, it's allowed, .word OX16, that will put a word of data into your instruction stream, and if your microbit tries to run it, it might not do what you want. It might just do something random or crash your program. That's not what we want to do. Usually when we're storing data, we want to store it in a place that your program counter is not going to run over it and try to execute it. So that's why we use this data directive, which is on purpose storing some data elsewhere in our RAM, in a non-executable part of RAM, starting at OX2 followed by 7 zeros, so that the microbit doesn't accidentally execute that data. It is in fact stored in Flash and then copied out of Flash into RAM at the start of your program. So now that we have the memory viewer open, this is the Flash part of memory I've just viewed, and my incredibly long sentence is in here. Here's an incredibly long sentence. It's been stored there and then marked to be moved into RAM by my startup script at the start of my program, so that I can access it in the correct way. Yes, so as a zoomed out way of thinking, all of these things, data and instructions, they are all zeros and ones encoded somewhere in your microbit, stored in Flash, stored in RAM, stored in places that are executable, stored in places that are not executable, and you just need to keep a mental model of where these things are going to end up in your program. So we've talked about the data section, or we've used it so far, but just to be really clear, the data section lets us store stuff in SRAM during our program. It's not executable. It gets moved into RAM where we can load it. So that data assembler directive, and we often use a label to access the stuff we've put into data. What does this do? Letter R0 is going to load the address of R0 which is the address of stuff, into there, which will be OX2 followed by 7 zeros. Letter R1 will load that word OX dead beef into R1. R0 won't be changed. This is stuff we've done a lot. But just to point out that in our startup script, this code, startup.s, this code actually runs before main on your microbit. I'm just going to close some things, got too many things. And I'll save, okay. The first thing that happens when your code runs is that a special function called reset handler runs. We'll explain later in the course why that happens, but from the microbit's perspective, it starts with a reset. It's just been reset and turns on, and it starts in its starting place, which is called reset handler. Then the first thing that happens in this startup file is setting some stuff up for the stack. We'll learn about that next week. And the second thing that happens is that we copy data from Flash to RAM that have been marked as being data things. So we've got some labels here that have been preset up by the linker to point to different parts of Flash and RAM that are where we have to copy that data from the Flash into SRAM. When we flash the disco board, when we upload the program, it can only put stuff into Flash, right? Because the Flash is our non-volatile storage. It's storage that stays even if you turn the microbit on and off. If it copied stuff into RAM, it would disappear as soon as your microbit was reset. So we can't do that. All of the data that you put in .data sections gets put in Flash initially, and then this procedure in the startup script copies it out into SRAM where we can read it and change it as we want. Yeah. Then you might ask, can I use sections for more code in my, is there a code section in my file? Well, it's the default, but actually it's called .text. That's the normal code section for storing code. And the linker puts all of your .texts together and puts that in an executable code area and puts all your .datas together into a place that's going to get copied into SRAM by the startup.s program. And that's the end of the lecture. I was only 5 minutes longer than I thought I would be. So thank you for joining me this morning. Folks, I'm going to say goodbye quickly and get on to the next thing, but I hope that you enjoyed our little adventure with strings, our little discussion about subtraction, and I'll catch you folks on Monday for our first lecture on functions. Please, everybody, don't forget that you must work on your assignment pre-submission task this week, or in preparation for your next lab. So until Monday, have a great weekend. See ya. It's only Thursday morning. We don't need to have a great weekend yet. Have a great rest of Thursday and all of Friday, and then have a great weekend is what I should have said.